Hey there, let me ask you something. When you see the word pure on a carton of milk or a bottle of juice, what do you think that actually means? Well, today we're going to dive into that exact question, and I got to tell you, the scientific answer, it's probably not what you're expecting.
Right? I mean, you see it everywhere. Pure ghee, pure spices, pure mineral water. And for most of us, we just assume that means, it's good for us. It doesn't have any weird stuff mixed in, no additives. But what if I told you that from a scientist's perspective, pure means something totally different? So here's the big twist. For us, pure means no junk added. But for a scientist, it's way more specific. For them, a pure substance is made up of only one single type of particle. Every single particle is chemically identical to every other one. Think about that for a second.
Yeah, this flips everything we thought we knew completely on its head. So that carton of milk in your fridge, the one that says 100% pure, well, to a scientist, that's not pure at all. It's actually a super complex mixture of things like water, fat, proteins, you name it. And that right there is the key. So if most of the stuff around us isn't scientifically pure, then what is it?
Well, it turns out pretty much everything is a mixture. We're living in a world of mixtures. The air we're breathing right now, the ground we walk on, it's all just a bunch of different pure things all jumbled together.
The official definition is actually pretty simple. A mixture is just when you have more than one kind of pure substance all in the same place. A great example is seawater, right? It's water plus salt plus a bunch of other minerals all mixed in. And here's the really important part. They're just physically mixed. They haven't chemically reacted and bonded to become something new.
Okay, so even mixtures aren't all the same. They basically come in two flavors. You've got your homogeneous mixtures. Think homo meaning same. Everything is so perfectly blended that you can't see the different bits. Salt dissolved in water is a classic example. And then you have heterogeneous mixtures. Hetero meaning different. And with these, you can absolutely see the different parts. Like if you pick up a handful of soil, you can see the little rocks, the sand, the organic bits. It's not uniform at all.
But wait, there's more. We can get even more specific. Let's zoom in a little closer and look at three very specific kinds of mixtures that you definitely deal with every single day. Solutions, suspensions, and colloids. All right, first up, solutions. You can think of a solution as the ultimate smooth blend. It's a perfect homogeneous mixture. The particles of whatever's being dissolved, we call that the solute, are just so incredibly tiny that they basically vanish into the liquid, which we call the solvent. And once they're dissolved, they're not going anywhere. They won't settle out to the bottom, and they're so small they can't even scatter light. Now, on the complete opposite end, you have a suspension. This is a classic heterogeneous mixture where the particles are way bigger. The perfect example is muddy water. You can literally see the bits of dirt floating around. And what happens if you just let it sit for a while? Yep, all that dirt settles right to the bottom. It's what we'd call an unstable mixture. Okay, so you've got the perfectly mixed solution and the chunky suspension. But what about the stuff in between? Well, that's where things get really interesting. Meet the colloid. This is the tricky one. A colloid, like our old friend milk, looks totally smooth and homogeneous, but it's secretly heterogeneous. The particles are bigger than in a solution, but they're still just small enough that they don't settle out. They just hang around, suspended.
So if it looks like a solution, how do we know it's a colloid?
There's a cool trick for that, and it's called the Tyndall effect. It turns out those suspended particles in a colloid are just big enough to scatter a beam of light. So if you shine a light through it, you can actually see the beam's path. A true solution, with its super tiny particles, the light just passes right through. No visible beam.
And I promise you, you've seen this in real life. You know when you're in a forest and you see those beautiful sunbeams cutting through the mist or fog? That is the Tyndall effect. The little water droplets floating in the air are acting like a giant colloid, and they're scattering the sunlight, making those rays visible. Pretty cool, huh?
Okay, so everything we've talked about so far has just been about physically mixing stuff together. But what happens when things don't just mix, but they actually react with each other? This, my friends, is where we get to one of the most important ideas in all of chemistry, the difference between a physical change and a chemical one.
Let's imagine a little experiment. Say you take some iron filings and some yellow sulfur powder, and you just stir them together. What you have is a mixture, right? You can still see the different parts. The iron is still iron. You could even pull it out with a magnet. But what if you heat that mixture up? You heat it until it glows red hot. Suddenly, a chemical reaction happens, and what you're left with is not a mixture anymore. It's a completely new substance, iron sulfide. It isn't magnetic, and it doesn't look like iron or sulfur.
Something brand new has been created. So this table really nails the difference. In a mixture, things are just hanging out together. They keep their own identities, and you can usually separate them pretty easily. But in a compound, elements have reacted to form something brand new. It has a fixed chemical recipe, and its properties are totally different from the original ingredients. So mixing is a physical change, but creating a compound, that's a chemical change, a huge difference.
Okay, now that we've got that crucial distinction down, let's circle all the way back to our original question. What do scientists actually consider to be pure?
Well, there are two types of pure substances. The first one is an element. Think of elements as the absolute basic building blocks of matter, like the letters of the alphabet. You just can't break an element like pure iron down into anything simpler by chemical means. It's just iron. That's as simple as it gets.
And this second type of pure substance is a compound. This is what we get when elements react and chemically lock together in a very specific, fixed ratio. Water's the perfect example. It's always two hydrogen atoms bonded to one oxygen atom, H2O. And even though it's made of different elements, it's considered a single pure substance because that chemical structure is consistent throughout. So let's tie it all up. That milk we started with, a mixture. The air we breathe, a mixture. Soil, definitely a mixture. But pure water, that's a compound. Pure table sugar, also a compound. And a bar of pure gold or iron, that's an element. And just like that, you now have the scientific toolkit to correctly classify pretty much everything around you.
So take this new knowledge with you. Look around. The steel in your phone, the soda you're drinking, the clothes you're wearing, they're pretty much all mixtures. So I'll leave you with this question. Now that you know the science, what's the most surprising mixture that you use every single day? Something to think about. Thanks for tuning in.